So welcome back for lecture 4 of nuclear materials. Last lecture we were introduced to metallic uranium, its crystal polymorphs, and the phenomenon of thermal cycling growth. Well, this lecture, lecture 4 part 1, will continue on this topic and look at the other properties of metallic fuels and their respective radiation effects. So let's go to the top of page 36 in your notes, and you will see a graph of thermal conductivity as a function of temperature. And this is for polycrystalline uranium. Now there is a clear increase in thermal conductivity with temperature here, which is one of the reasons why running a reactor at a higher temperature gives improvements in efficiency. Here specifically, increasing the operating temperature gives us improved transfer of that heat to the cladding and out to the coolant. Now, as we've said before, good thermal conductivity is essential to a fuel, as the linear power rating of a fuel element is generally limited by this thermal conductivity, as we must avoid it melting whilst maintaining a good thermal efficiency. But as we'll see, such an increase in thermal conductivity with temperature is not the same for all fuels, most notably uranium dioxide, our metallic counterpart. But not only does metallic fuel have good thermal conductivity, but it shows good ductility, as shown in the figure at the bottom of the page, which makes it far easier to fabricate in comparison to its ceramic competitors. And this is one of the key reasons why metallic uranium is still used in some reactors. Of course, such properties will change upon alloying and after irradiation, but that's for later. So how does uranium fend against corrosion? Well, it reacts readily with most environments, unfortunately, including air and water. The oxide that forms on the surface is not particularly protective, as it cracks and crumbles under temperature as it thickens. And at low temperatures in water, it can provide some protection, though again, this is lost at higher temperatures. So it's quite tricky in terms of corrosion. But one key phenomenon we need to look at is irradiation growth. Irradiation growth is similar to thermal cycling growth in that it is growth under constant volume. However, its origins are obviously in irradiation, and some aspects are actually quite unique. Now, irradiation growth occurs without the need for stress and at relatively low temperatures below, say, 300 degrees Celsius. Okay. Now, under a neutron flux, even single crystals of alpha uranium show irradiation growth. And it's accompanied by hardening and embrittlement, all of which arise due to the formation of dislocation loops, interstitials on the 010 plane, and vacancy loops on the 110 family of planes. And these form on different planes on account of the localized heating caused by displacement cascades, coupled with the anisotropic coefficient of thermal expansion. Now, consider how heating a single grain experiences stress. The grain experiences tension where the coefficient of thermal expansion is negative. In this case, the 010 direction. Interstitial atoms then preferentially condense on the 010 plane to relieve that tensile stress. And you're going to get the analogous effect occurring for vacancy loops. Now that might seem quite strange and sort of counterintuitive, but this leads to a net expansion parallel to the 010 direction. Nice. So I can see why that's counterintuitive, but you can see this on the figure on the following page, page 38. This net expansion parallel to the 010 direction. Now, you should note, however, that this effect isn't seen if the material is polycrystalline with no texture. Individual grains would change shape, but there would be no net shape change. Okay. That's radiation growth. Further to irradiation growth, you've got irradiation swelling. And that's different to the growth phenomenon we've mentioned, as swelling involves the increase in volume of the material. And the rate of swelling is governed by temperature, with two significant regimes. At lower temperature, swelling is largely due to anisotropic irradiation growth, causing internal stresses that then lead to the formation of cavities and voids, increasing the material's volume. But at higher temperatures, gaseous fission products are the greatest influence, forming bubbles and causing gas-assisted void nucleation, which I mentioned before, and that leads to rapid swelling. Now for uranium, the three phases will behave quite differently in terms of swelling on account of their symmetry elements. In addition to the temperature effects I've described, as shown in the figure here, the higher temperature gamma phase will exhibit a significant increase in swelling rate at higher temperatures, but the swelling will look very different microstructurally. And that's what you see here. As shown here, on the right-hand micrograph, we've got cubic uranium with rounded voids, indicative of swelling in a cubic microstructure. On the left-hand side, we have the faceted voids of the alpha phase, again because of its reduced symmetry. And as I mentioned before, swelling rates can be extreme, as shown in the graph below, with volumes almost doubling in some cases. So really quite a significant effect, irradiation swelling. But I've got something else to lay on you. Irradiation creep, another phenomenon you've got to understand. And there are two types of irradiation creep. Radiation induced creep and radiation enhanced creep. Radiation enhanced creep is, you've guessed it, creep at high temperatures where thermal creep would occur, but it's just exacerbated by radiation, with creep rates often being accelerated by factors of 10 to 100 in comparison to thermal creep. And the origin of both is the production of vacancies, because as you may know, creep depends on diffusion, and an increase in vacancy concentration increases that diffusion rate, in turn increasing the creep rate. Now in the case of radiation-induced creep, creep is occurring at lower temperatures than that of thermal creep, again because of the production of vacancies under irradiation. And when coupled with an applied stress, that can lead to creep. So a material may well be creep resistant at the operating temperatures, but when irradiated, we have to take special considerations. A material might seem thermally creep resistant, but when you get involved with irradiation, you will see some creep because of this irradiation-induced creep. And the graph at the bottom of page 40 illustrates the stages of this creep. Irradiation affects both primary and secondary creep. You're welcome to read further on the basics of creep in your own time. All you need to remember is that in primary creep, your strain rate is high, but reduces with time as the material work hardens. In secondary creep, the strain rate is constant. You can read the rest in your own time. And that concludes our foray into metallic uranium. We've been introduced to thermal cycling growth, irradiation growth, creep and swelling, and observed that the crystal structure of our uranium plays a significant role in any radiation effects. What we'll look at next is plutonium and thorium. Although given similarities with uranium, we'll only briefly summarize these. So plutonium-239. Plutonium-239 is our major fissile isotope with a significantly high fission cross-section. And much of our energy at a reactor's end of life is actually produced through the burning of this plutonium. But enriched plutonium can be used as a fuel at the start of life, such as reactors used for space applications can use enriched plutonium. Of course, to enrich plutonium, you've got to produce it first by the transmutation of uranium-238, and then, as we'll discuss later in the course, you've got to go through the enrichment process of segregating it from other species present in the fuel, which is quite expensive. Nonetheless, regardless of those costs, it is of appeal for a number of applications, such as space, like I said, but also breeder reactors. There are 6 phases of plutonium, and each is only stable over a very small range of temperature. It's monoclinic at room temperature, and orthorhombic, BCC body-centered tetragonal, and body-centered cubic as the temperature increases. As with uranium, such phase transitions during temperature changes are going to be a major problem. So stabilizing the high temperature phase is going to have great advantages. However, plutonium has a very low melting temperature. It's only around 640 degrees Celsius, so pure plutonium is not really favoured for high temperature applications. Now the graph below here, in the centre really, shows the differing densities for the 6 phases. And as you can see, these differences are quite significant, meaning that great changes in volume are going to occur during these phase transitions. Not only that, but plutonium is highly toxic, pyrophoric, as well as being very sensitive to corrosion. So it's a real challenge to work with. However, you can alloy it. You can alloy it with zirconium, for example. That can help to increase the melting temperature and reduces problems with interdiffusion with any stainless steel cladding you might be using. But this can only really limit it to an extent because, as I'll show later in the course, compositional changes over time across a fuel rod does occur, and it will enrich some areas in plutonium, and so you'll start to lose the benefits of the alloying because it'll get segregated. But what about thorium? I mentioned that before. Well, thorium is a potential fuel. Although it's been considered since really the beginning of the US weapons program, there continues to be quite heated debates regarding the benefits of thorium versus uranium. Thorium isn't fissile. Thorium-232, the only naturally occurring isotope, is fertile, but produces fissile uranium-233 upon neutron capture. And one of the key benefits is its abundance, really. That's why thorium has a huge selling point. It's thought to be about 3 times at least more abundant than uranium in the Earth's crust, with most rocks and sands actually containing minute amounts of thorium. Other than that, the key benefit is the fission of the uranium-233 that's produced from thorium. Well, that fission event produces more neutrons per fission than the fission of uranium-235, meaning that in the end you've got more neutrons to work with. But indeed, it's a more challenging reaction to control because you've got that greater number of neutrons. Furthermore, scientists claim that the proportion of long-lived actinides is reduced enough to make spent thorium fuel easier to store, although again that's been debated as well. In terms of its mechanical properties, or material properties actually, it's got 2 phases, both cubic, with a high melting point of around 1750 degrees Celsius. It's pretty sensitive to corrosion, but not as bad as plutonium. It's readily adapted to applications by alloying. The main constraints in its commercial application, like many things in nuclear, is that significant research and development are needed, and producing and reprocessing the fuel is quite expensive as well. And the last point really would be uranium-233 becomes contaminated with uranium-232, which decays to produce rather aggressive gamma emitters, which make it a bit more challenging to handle than its counterparts. And really, that's metallic fuels. So now you should know, if you go back over at least, you should know the advantages and disadvantages of the three principal metallic fuels considered in reactor design, and the radiation effects that we can observe for those. But as I mentioned before a number of times, it is ceramic uranium, uranium dioxide, that's the most common commercial fuel. So we're going to spend part 2 of this lecture covering ceramic fuels. We'll spend a bit more time on those. So I'll see you shortly for lecture 4, part 2.